Okay, guys, so I decided to come back and record some little bit of bonus content for you with the two small things that were left out of the main lecture video. The first one is about this illustrative example of a null hypothesis. There is no life on Mars, right? This is just an illustrative example in order to try to drive home a little bit more this idea of having a null hypothesis instead of an actual hypothesis, right? Which is actually coming. So suppose we're gonna do some research to determine or to try to find life on Mars, right? And so our null hypothesis is not that there is life on Mars, but that there is no life on Mars. And why is that? The current knowledge that we have right now is that there is no life on Mars. So we are bound to take this as our null hypothesis because we really don't have any other option right now, because we don't know. We can't affirm that there is life on Mars because the current knowledge that we have and the knowledge that we are trying to change, so to speak, by running an experiment is that there is no life on Mars. So what are the possible outcomes of an experiment like this? Well, one possible outcome is that we reject our null hypothesis. So we destroy it, so to speak, right? We make it so that it's not true. We show that it's not true, which means that there is life on Mars. Or we fail to reject our null hypothesis. In that case, we can't state conclusively that there is no life on Mars. All we can say is that we haven't found it yet. So as far as we know, so far, there is no life on Mars. Now, suppose that I actually make an experiment to try and reject this hypothesis, right? I really want to find life on Mars and I really want to reject this hypothesis. There is no life on Mars. So let's say humanity sends 10 spaceships to Mars. Each one has one astronaut, and this one astronaut is going to, like, these ships are going to land in Mars in different places, right? Randomly distributed throughout the planet. So it's like a random sample of the surface of Mars. Then the ships are going to land, and then the astronauts are going to come out of the ships, and they're going to walk around a certain area that's well defined, because this is an experiment, so you can't just go there and do whatever they want. They have to follow a certain protocol, a specific protocol that defines the experiment. So let's say that the protocol says that they're going to get out of their ship and they're going to walk in circles in a certain area, right? And not all of them will do the same thing. Now, if no one managed to find any traces of life on Mars, then, well, we failed to reject our hypothesis because we could not find any evidence to the contrary, or we could not find any strong evidence that would point to the rejection of our hypothesis. So we are forced to maintain our hypothesis. So the current knowledge stays the same, okay? Again, we are not accepting the null hypothesis. We're not stating that the null hypothesis is correct, period. We're just saying there is no evidence to reject the null hypothesis. So it remains the same for the time being. However, if one, let's say, bacteria or one virus or one small worm or something like this, or a little mushroom or something like this is found on Mars, just one, that's all we need. One bacteria found on the surface of Mars, that is enough to completely reject the null hypothesis. And then we can say for sure there is life on Mars. We rejected our hypothesis. The hypothesis is wrong. And yes, there is life on Mars. So, and then if we ask ourselves again, like I suggested before, does the evidence, so in this case, the evidence is like the life that we found, the bacteria. Does that evidence make my null hypothesis look ridiculous? Yes. Because if my null hypothesis is that there is no life on Mars and I actually found life on Mars, then the hypothesis is ridiculous. And therefore, it's not truth, it's rejected, okay? So it only takes one example to make the null hypothesis look ridiculous, and then you reject it. But at the same time, I could not confirm it. I could not say, so just think about that. I could not say that there is no life on Mars. I could not say conclusively that there is no life on Mars, and my null hypothesis is definitely right, because even though I took a random sample of the surface of the planet, maybe there was something under a rock somewhere that was outside of the sampled areas. Maybe, I don't know. I cannot say that anything about what I did not, I mean, I cannot say anything about the areas where we did not check, right? Because, and it's okay, because no experiment is perfect, right? So there will, unless we comb the entire surface of Mars, every single like cubic centimeter, and in every depth possible, we cannot, there will always be some part of Mars that we did not check, right? So that's why we cannot say for sure that there is no life on Mars. So we cannot confirm our hypothesis. All we can do is either reject it or fail to reject it. And that's the same for you. Whenever you come up with your null hypothesis, you got to think, I will either reject it if my data makes my hypothesis look ridiculous, or I will fail to reject it, which in which case the data could have been true given the null hypothesis. So it's reasonable to expect that given that the null hypothesis was truth, the data is reasonable or is not that different than expected. And then you fail to reject it. So these are the only two outcomes that are possible. Now, there's another concept that's also important, not as important as the null hypothesis, but still interesting, which is the alternative hypothesis. In this case, it's H1, while the null hypothesis was also known as H0. You can also define an alternative hypothesis in addition to your null hypothesis, although that's, for our specific assignment, that's not entirely necessary, but you can also. So what happens is that in both cases, both when you have a one sample or two samples, so if you just gather some data and then measure something, or if you have two samples that you're comparing, in both cases, if your null hypothesis is rejected, there are three possible alternative hypotheses that could have happened, right? So the first one would be that the measured value, or the difference between the values, doesn't matter, is simply different than the initial hypothesis. So if your hypothesis was that the value was X, then you can have an alternative hypothesis that says the value is different, period, right? Or you can have a more strict alternative hypothesis that says the measured value or the measured difference is either smaller or larger than the null hypothesis, right? So what is important to understand about the alternative hypothesis here is that the alternative hypothesis doesn't really affect the experiment that much, right? Or the results or anything like that. The alternative hypothesis is just something that you expect to be truth in case the null hypothesis is rejected, right? And that's just one way to kind of like measure or determine whether you were right about whatever you were expecting to happen, right? Because you see, let me give you an example that's a little bit more practical, right? Suppose you're testing something that so you're doing your thesis and you build a new digital solution for whatever, like we discussed in the beginning of the lecture. And then suppose you finish this, you have your prototype, then you go and you tested prototypes. So you have two groups of people, let's say two groups of 20 people. One group is not using your new prototype. The second group is using your new prototype, right? And then you measure that. So you measure the performance, whatever kind of performance could be, anything that you define as being performance. Determine the performance of group one, determine the performance of group two. Now, suppose that, of course, your null hypothesis, as we discussed before, is that both groups will have the same performance because your new tool doesn't help at all. So that's the current knowledge that we have. That's the only thing we can assume beforehand. So that's your null hypothesis. Then suppose you measure the performance and then you realize that actually no, the two groups have different performance, right? Now, for some experiments, that is enough. For some experiments, all you have to know is that it's different and you don't care too much about whether it's larger or smaller. So in that sense, that would be your alternative hypothesis, your H1, is that they're simply different. I've rejected the null hypothesis. That's all that matters to me. Some experiments are, for that is completely enough. In your case, that is not enough. In that case of the example, why not? Because you need the performance of the group which is using the tool to be better or larger than the original one, the people who are not using your tool. You need them, you need that to be different, or sorry, larger, because there is a possibility that the people who used your new prototype actually did worse than those who did not use it. And that would be a big problem for you, because that would show that not only you did not improve, but you actually made it worse than not using it. So you see, this is a conceptual decision that you have to make when you're determining your experiment. What is my alternative hypothesis? Do I care if the value is larger or smaller? That will not affect at all the actual design of the experiment, how you do the experiment, because the data gathering will be exactly the same. You're going to gather the data, you're going to measure it, and you're going to do what you have to do. The only difference is on how you interpret the data later, because you can then later say, yeah, my alternative hypothesis was that the performance of the group with the prototype would be larger than the performance of the group without a prototype. And yes, I got it right. The alternative hypotheses actually have shown that the performance is larger. That's good, but it could also be that you actually got it completely wrong and then it became smaller. And then it's completely conceptual, because performance depends also. It could be that performance for you is actually that people will do something faster. So faster means that if you measure time, then you're actually measuring, you want this to be smaller. So you want to be less time than more time. So you want your group with the prototype to actually have a smaller time than the group without a prototype they will take longer to do something, right? So in that case, you see how it's completely conceptual, because in this case, smaller is better. While in the previous case, if you had some kind of a performance measure that you're measuring, then larger is better. So the actual handling of the experiment didn't really change that much. You still measure something, you'll still have your experiment. It's just that when you define your alternative hypothesis, you're just making it clear what is expected if the null hypothesis is rejected: smaller, larger, or simply different.